Hello, everyone, and welcome to today's webinar on making safe and accurate high-power measurements. Your microphones will stay muted throughout the session. If you have questions, we will address them at the completion of the presentation using the Q&A feature of WebEx. However, you are welcome to type in questions at any time. Please send the questions to both the host and the presenter so we can respond. Our presenter today is Mike Hoyer. Mike is an applications engineer for HBM with a Bachelor's of Science degree in electrical engineering from New York Institute of Technology in Old Westbury, New York, and an associate's in engineering science degree from Farmingdale State University of New York. Mike has over 35 years of radio broadcasting experience and over 30 years of data acquisition, marketing, and applications engineering experience in the automotive, aerospace, and power industries, providing solution-oriented results to customers worldwide through articles, trade shows, seminars, videos, webinars, white papers, and on-site training and demonstrations. Mike, it's all yours.
Well, thank you very much, Krista. Actually, I started as an application engineer for Nicolet's high accuracy and high speed data acquisition solutions back in 1991. And I like to introduce myself and say that, well, here I am 3 or 4 acquisitions later. In fact, the last acquisition was actually a merger, which leads me to a question I'd like to answer. Who is HBK, which is the logo you see on the bottom right of your screen? Well, the quick answer is HBM is a leader in test and measurement solutions for more than 70 years, recently merged with sister company Brüel & Kjær, or B&K for short, a leader in sound and vibration for more than 75 years. And as a result, HBM plus B&K equals HBK, the leader in integrated solutions for any test from a single provider. So what does this mean for you? Well, HBM product solutions include a wide variety of sensors, such as torque, force, strain gauges, data acquisition systems, including high channel count, universal rugged, and high speed, plus power analyzers, which we're going to discuss in more detail shortly, as well as amplifiers for industrial control and analysis software for fatigue, durability, and reliability. On the other hand, sister company B&K offers product solutions that include analyzers and analysis software for sound and vibration, sound level meters, NVH engineering services, complete vibration test systems, and acoustic end-of-line test systems, plus microphones and accelerometers. So with the recent merger, HBK can now provide you a one-stop shop or complete portfolio of all these solutions, which means shorter development cycles, optimized products, and better decisions. So HBM and B&K are now considered as brands under the HBK portfolio. So our agenda in today's webinar is to identify and explain the key factors that are going to ensure safe and accurate measurements in high power environments. And these include safety measures, voltage terminology, IEC categories, isolation, connectors, cabling. We'll talk about speed, accuracy, analysis, and calculations, and technical support. We'll also explain how these factors apply to some of the more common high-power applications, including high electric and magnetic fields, electric motors, generators, switchgear, and high-voltage impulse testing, producing some accurate calculations per the industry standards. Now, there are a variety of measurement applications that require additional safety and accuracy, which isolation systems can offer, including power and ballistic applications. And today we're going to be focusing on the more common power applications, including electrical motor and generator and electric grid testing, where you get involved in things like variable speed motors, up to 1,000 or more volts, hundreds of amps. There's switchgear testing, circuit breakers and fuses up to maybe 10K volts, 100K amps. Standards include STL, the Short Circuit Testing Liaison Agreement, and UL 489, we'll talk more about that. High voltage impulse testing, transformers and surge arresters, dealing with 100K to millions of volts, basically simulating lightning. Standards include the IEEE and IEC impulse measurement standards. One of my favorite applications is the lightning monitoring systems at Kennedy Space Center for spacecraft in Florida, where you're dealing with millions of volts. It's very similar to the impulse testing. In fact, the Endeavour was struck at least 11 times, delaying the launch back in July 11, 2009. And actually, today is a bit of history in the making. For the first time since 2011, 2 American astronauts are going to be heading to the International Space Station from a U.S. SpaceX rocket, the Dragon capsule, from Pad 39A at NASA's Kennedy Space Center, scheduled for 3:33 this afternoon, Central Time. So go SpaceX. Well, all the high-power applications we just mentioned have unique and common challenges, such as high voltage, which contains high electrical fields, and or high current, which contains high magnetic fields. Now, our biggest concern in this type of environment would be safety for the user and the equipment, making a reliable and accurate measurement, and be sure to get the results and the support needed. So our objective in this webinar is to address and meet these challenges and concerns by, well, first identifying and then explaining the key factors that are going to ensure a safe and accurate high-power measurement. Now, these include isolation, which ensures the safety of both you, the user, and equipment, and eliminates ground loops. High speed and high accuracy, which enables accurate measurements to meet industry standards. Analysis, to obtain calculated results and produce answers to the industry standards. And of course, technical support with a proven track record assuring customer-oriented solutions. Now, before we talk about these key factors in more detail, let's first talk about safety measures. In fact, we'll begin with the most important concern, safety. Some or most of this may seem obvious, but it's important enough to remind ourselves to be safety conscious and be aware of the danger involved. For example, measuring voltages above 50 volts DC is considered dangerous and requires special precautions. In fact, the risk of electric shock occurs when the voltage between active parts and ground is greater than 50 volts DC or greater than 25 volts AC, and short circuit current greater than 12 milliamp DC or greater than 3 milliamps AC. In fact, OSHA and other related agencies mandate measurements above 50 volts DC are to be performed by trained, qualified, and authorized personnel. So you need to know the rules and limits for each CAT code, and we'll talk more about those CAT codes in a moment. Never connect to live or energized circuits and assume they're off. Wear safety glasses and safety gloves and be safety conscious. And I like this handy tip. Be sure to use one hand when making measurements, because the last thing you want to do is have one hand on a metal pipe while using your other hand to connect to a high voltage point. So let's touch a bit on voltage terminology. Exactly what does it mean when somebody says, I want to measure 120 volts AC? Does that mean RMS, peak, peak to peak, phase to ground, phase to phase? You should always check and ask whenever someone states a voltage or a current in order to determine the actual amount of voltage or current involved. Now, the diagram on the right shows the relationship between RMS, peak, and peak to peak, such that 120 volts RMS is about 170 volts peak, which is about 340 volts peak to peak. Generally, in the power industry, voltage level is an AC RMS value, and in other fields, voltage level is an AC or DC peak. Again, don't assume, always ask. Now, the IEC has established safety requirements for electrical equipment for measurement, control, and laboratory use. And in doing so, they've established a list of categories, or you can call them CAT for short, which identify RMS overvoltage levels or categories where an instrument can be connected. So, for example, CAT 0, which was CAT 1, is not directly connected to the main, so, for example, connected to secondary circuits. CAT 2 is directly connected to low voltage mains, for example, a wall outlet. CAT 3 is directly connected to distribution or low voltage mains. Other common example would be circuit breakers. And CAT 4 is directly connected to the source of low voltage mains, or, for example, electric meters. Now, just a quick note on connectors and cables. You want to be sure to avoid using connectors and cables with exposed metal contacts, and instead be sure to use connectors and cables that do not have any exposed metal or contacts for ultimate safety. You also want to avoid using BNC cables above 500 volts peak, because that's their maximum rating. In fact, banana connectors and cables are designed for higher voltages. Now, we've all probably floated an instrument. I know I did once in our lifetime, actually. Before floating an instrument many years ago while in college, I was designing an AC regulator circuit. And immediately after attempting to measure the AC output with a scope probe, I saw a spark trip the breaker because I shorted the AC output to ground. So then I decided to float the instrument, as they say, not realizing there were lethal voltages on the case of the instrument. Unfortunately, I still hear from time to time people floating an instrument in order to make a high voltage measurement by disconnecting the earth ground of the measuring device. Unfortunately, this creates a huge safety issue. In fact, it's unsafe for the user because you have potential lethal voltages on the system's chassis. And it's unsafe for the instrument because it subjects the internal electronics and power supply to additional stress, causing operational problems and a measurement quality issue. So, what is the solution? Well, the solution is to use isolation. This is going to ensure the safety of you, the user. It places a barrier between the user and the high voltages, and also safety for the equipment, placing a barrier between the equipment and the high voltages. Now, please note that the barrier is only limited to the amount of isolation stated in the equipment specification. Also, the elimination of ground loops, noise, and additional errors prevents current from flowing between ground locations. We'll talk more about isolation in each of the different power applications in a moment. Now, here's a list of some of the typical methods used to connect high voltages to measurement amplifiers with isolation. If the amplifier does not include isolation, then you're going to need to add an additional system, an isolation system, in front of the amplifier. Now, the ideal and easiest high voltage connection, of course, is the direct connection for maximum accuracy and bandwidth. However, this is only possible when the voltage is within the input range of the amplifier. Now, another method is through the use of high voltage dividers and attenuators. You can gain high accuracy and sometimes high bandwidth, but you'll need to check the specifications. Of course, you'll need to open the wiring to install a high voltage divider or attenuator, and they do come at a higher cost. High voltage probes offer low accuracy, and sometimes they're difficult to use with isolated amplifiers. And a note of caution, the probe's ground clip does not attenuate the voltage. The positive tip of the probe is the only part that actually attenuates the voltage. So be sure and keep that in mind. It's one of the drawbacks of voltage probes. Even though they come at a lower cost, they do have several drawbacks. Now, often measuring current is more challenging, especially when it comes to accuracy. In fact, some of the more typical methods for measuring current include inductive transformers. However, they only offer AC measurements, low bandwidth, and low accuracy. Shunts, although offer very high bandwidth and medium accuracy, are challenging since they not only require opening the wiring to install, but they require isolation. And they place stress on the amplifier due to a small millivolt output being measured on a high potential. Hall effect, or often called current clamps, are easy to use and connect. However, they usually offer low bandwidth and low accuracy. Rogowski coils offer high bandwidth measurements and are also easy to use. However, only offer AC measurements and at a low accuracy. Finally, the best alternative for high accuracy and medium bandwidth is the zero flux CT. It's often used for efficiency measurements in electric motors and drives. And now that we've covered some of the more important terminology, we'll apply what we've covered to some of the more common high power measurement applications we mentioned earlier. Well, an example of a high power measurement application would include electrical motor and electric grid testing. Now, today, there's an ever-growing set of applications using variable speed electric motors or generators, including appliances, cars, buses, forklifts, planes, pumps, trains, and wind energy, just to name a few. In fact, in this example, we're going to focus on a vehicle's electric drivetrain, which could be any power application that requires the measurement of up to, let's say, 1,500 volts, sometimes even more. So in this example, you'll often need to measure at the output of the power source or battery, as you see on the left. In fact, voltages up to 1,000 volts DC would be measured, currents up to 300 amps DC, and then at the output of a frequency inverter in the middle, you'll need to measure n number of phases of voltages up to maybe 1,000 volts AC, and n phases of current, maybe up to 500 amps AC. Now, in fact, in this application, you might also measure torque, speed, position, so that you can actually calculate the mechanical power in addition to calculating the electrical power at the input and output of the inverter, which enables you to ultimately calculate the efficiency of the entire system or electric drive, or in reverse, efficiency of the generator. Now, to do so, this requires high accuracy measurements. So here's an excellent solution to directly connect and acquire high power signals in electric motor, generator, or electric grid tests up to plus minus 1,500 volts DC, or sometimes more, using this high accuracy and high bandwidth power card in conjunction with shielded high voltage cables for low noise measurements. Now, the power card has 3 inputs for voltage and 3 for current. So the more phases you have, the more power cards you add to your 2, 3, 4, 7, or 17 slot mainframe. Now, the power card has an accuracy of 0.015% of reading and can measure up to plus minus 1,500 volts DC. Or with an accuracy of plus minus 0.2%, you can measure up to 5 kV RMS with the optional differential probe, as now seen at the bottom right. Also, currents can easily be measured using the power card's internal high-accuracy burden resistors, which support all the common zero-flux current transducers. The power card has been tested up to 7.4 kilovolts, which allows for safe measurements up to 1,500 volts DC and 1,000 volts Cat4. The card offers many predefined calculations for RMS, P, S, Q, lambda efficiency, THD, DQ0, and much more. Plus, you can also write your own custom real-time equations. Now, every voltage and current channel is sampled at 2 million samples every second, and it has up to 18 bits of vertical resolution. Speaking of vertical resolution, here's a slide that clearly shows the importance of high vertical resolution. And actually, this diagram is the result of an experiment I did many years ago, acquiring the offshoot of a switching power supply at PowerUp. And what I did is I used a measurement system that had both an 8-bit and a 12-bit digitizer in the same system. And so I acquired the data at the same sample rate and equally expanded both waveforms. Now, the 8-bit signal shows nothing but horizontal lines at each digitizer level due to the low vertical resolution. However, you see the 12-bit signal, which has 16 times more vertical levels or higher resolution. You can clearly see the switching frequency of the power supply. So the chart just above the diagram gives you an example for comparing the smallest resolvable voltage based on the vertical resolution of each digitizer, for example, 8, 12, 14, 16, or 18, over a 20-volt full-scale range. Now, often the largest amount of error in many power applications, including electrical motor or generator testing, is in the measurement of current. Therefore, special attention's got to be used to maximize accuracy and stability and minimize noise. So first, it's important to select a high accuracy and high bandwidth sensor. Often the sensor includes a power supply to power the sensor and the necessary low noise shielded cabling from the sensor to the power supply. In fact, the output of the power supply often has a low current output, and to minimize this noise, you need to use high voltage shielded and isolated cables, as shown in the diagram, to shield and isolate the low current signal from the noisy environment. Now, we offer a complete line of HBM branded high accuracy current sensors and low noise, high voltage shielded cables for the entire measurement. Now back to our electric motor or eDrive example, electric drive example. Here we see a power analyzer solution recording all the signals involved, including electrical, such as voltage and current, mechanical, including torque and speed, physical, such as temperature and vibration, and even digital, like a vehicle CAN bus, and accurately performing all the desired calculations in real time, even during speed and frequency changes of the motor and inverter. So how is this possible? Well, all calculations across the entire drivetrain must be done on an integer number of cycles in order to produce accurate results, such as true RMS measurements. Digital cycle detection locates zero crossings instantly, which enables accurate and real-time results even during speed changes. For example, in the diagram at the bottom, the blue signal is one phase of current increasing in frequency. The red waveform shows the detected zero crossings on the current for every cycle, and the red waveform is then used as a cycle master to accurately calculate for every full or half cycle, you decide, the true RMS voltage or current, or even calculate the electrical power over the same cycle as the mechanical power. And that's going to eliminate the common efficiency error or of greater than 1, which often happens due to misalignment of the calculation in electric drivetrain measurements. In fact, this technique enables calculations to be performed even when the frequency of the phase of current changes due to dynamic load changes. For example, motor startup, slow down, going up a hill, or down a hill. So to wrap up this application, you can visit our website for complete electric power testing solutions, including power analyzers for R&D advanced analysis, or power meters for cost-effective entry-level solutions for either eDrive or eGrid applications, plus details on all the accessories for a complete solution, including torque sensors, current sensors, cables, etc. Be sure to visit our eDrive landing page at www.hbm.com/eDrive, short for electric drive. And that's going to offer a nice overview, plus an 8-minute video introducing the eDrive solution and a link to the HBM knowledge base, which includes things like videos, for example, on electric machine testing, DQ0 and space vector. There's even white papers on power measurements on a 6-phase motor. There's webinars, for example, fast efficiency mapping of electric drives, application success stories, such as making electric motors more efficient. And there's even a contact form where you can actually reach out to our electric machine experts. Again, the landing page is hbm.com/eDrive. Now, our next application is switchgear testing or circuit breaker or fuse testing. And this is a very demanding application with several challenges. For example, you're dealing with currents up to hundreds of kiloamps, which are interrupted while voltages of up to several hundreds of kilovolts are present, creating high electromagnetic fields. In fact, this requires specific hardware and software to produce accurate and reliable test results while meeting international standards. Now, some of the hardware challenges include isolation, amplifier drift, noise, electromagnetic immunity, and battery operation. There's even software challenges that include data integrity, repeatability, and productivity. Now, here's an example of a complete solution which is fully compliant with international standards and recommendations of the high power community. We have proven hardware designed to withstand severe electromagnetic and environmental conditions. There's a high-speed data acquisition system incorporating technically infinite isolation via a battery-operated fiber optic isolated digitizer. There's also a high-speed test sequencer for accurate sequence and timing control incorporating fiber optic isolated outputs and inputs. We'll talk more about these pieces in just a moment. Now, the software even conforms to relevant standards and recommendations, including STL, the Short Circuit Testing Liaison Agreement, and UL 489. There's also recovery voltage and asymmetric and symmetric current analysis. So first, let's start with the hardware. In this example, we have an isolated digitizer system, which starts with a fiber optic isolated transmitter at the test point. Now, for near infinite isolation, you can use a battery powered. However, for AC powered style, you've got a 1.8 kilovolt isolation capability. There's even extra shielding to withstand electric and magnetic field environments to minimize measurement interference. And then you have a fiber optic isolated receiver, which is at the control center and at the mainframe. You can have up to 800 meters of cable length, so quite a distance from the lab. But even if you have different transmitters at different locations with different cable lengths, there's no need to be concerned because the cable length correction prevents cross-channel skew, and that's done automatically. The whole system is completely controlled remotely via software and provides an accuracy of 0.1% full-scale range. The nice thing here is that you have up to 100 million samples per second per channel with 14 bits of resolution. Now, a device called a test sequencer is often used to control the operation of a test sequence for switchgear or ballistic tests. Now, this digital test sequencer shown at the top right, it replaces the traditional electromechanical systems with microprocessor precision. In fact, it offers up to 64 optically isolated outputs and 8 optically isolated start qualifier inputs. In fact, it's best to have a test sequencer that includes a set of qualifier inputs that will only start a test sequence if all the doors and the switches are properly set, ensuring additional safety to the equipment and the personnel running the test. Now on the right, you can see a sample overview of the software where you can set the timing of every optically isolated output controlling any array of switches during the test. Now the software provides complete control, display, and automated analysis and reporting capabilities. The STL analysis option provides fast and repeatable results in compliance to STL and UL 489 standards. In fact, the analysis includes transient recovery results on single or three-phase systems, plus symmetric and asymmetric current. On the right, you'll see a list there of some of the predefined STL and UL analysis functions. And in the STL operation manual, you'll find that each analysis function is referenced to the relevant paragraph in the STL technical report, and it provides a complete explanation with diagrams for each analysis function. Now, and since these labs often calculate results a bit differently, you can also easily create custom analysis equations using any of the STL and UL 489 algorithms and create a custom color report with waveforms and calculated results. So to wrap up the switchgear testing application, I'd like to mention that you can visit our landing page on the web, www.hbm.com/power, and you can click on the switchgear testing link. You'll see a complete overview of the solution, including isolation, timing. There's even a case study at ABB High Power Lab. There's also links to power and isolation products. In fact, you see this link here on the bottom left. You can also search, let's say in Google, and type in HBM video STL. You'll get a 15-minute video titled Genesis High Speed Perception STL Analysis Option for Switchgear Testing. And the video provides a nice overview on how to apply the STL algorithms to your testing needs. Our next application is high voltage impulse testing. And in this application, the challenge is that power grids are exposed to lightning strikes. So you've got damage to one or several elements that may result in a partial loss of power distribution, unsatisfied customers, and a high cost of repair. Here you're testing transformers, surge arresters, isolators, and switchgear, which is very important in order to prove the quality, and you need to actually prove it by documenting the component's electric strength. Now, this requires specific hardware and software to produce accurate and reliable test results while you're meeting the international standards. Here's an example of a complete solution which is fully compliant with the IEEE and IEC standards and consists of perfectly matched components. You've got a high-speed transient recorder with an integrated PC or tethered to your existing PC or laptop, incorporating a similar fiber optic isolation system as we described back during the switchgear testing application. You also have a high voltage 50-to-1 impulse attenuator, which has a large standardized LEMO style connector, which is found in most high voltage impulse labs. Then you have automated impulse analysis software, and this is going to increase your productivity and consistently will measure the parameters of impulse waveforms in accordance to the standards for IEEE and IEC. It's going to provide you reduced full voltage waveforms for superimposed visual comparison, and you can even make measurements and calculations that comply with current and new standards, including the K factor for the revision of the IEC standard. Now here you see a test setup starting from the middle of the diagram at the existing lab's voltage divider, labeled F. That's where we then connect to item E just to the left of F, which is the high voltage 50-to-1 impulse attenuator, which is able to accept up to 2,000 volts RMS. And here in this example, the 500 volts at the input is seen at the attenuator, and 10 volts is then at the output, which is connected to L just above E, which is a battery-operated, high-voltage, fiber optic isolated digitizer, or transmitter, which is going to output the fiber signal on the cable M, as in Mary, to the fiber optic receiver, N as in Nancy, which is connected to B, the PC running the software for control and analysis of the impulse test. So in this example, the advantages that you gain compared to a traditional test setup include there's no electrical connection between the test cell signals and the measurement equipment and the PC powered in the control room. So this creates a safe environment for both you, the user, and the equipment. There's also no equalizing currents between the test cell earth connection and the mains earth connection. Also, placing the impulse attenuator and the battery operated operated digitizer in the shielded control room, that means a minimum exposure to electromagnetic disturbances. Now, the software provides complete control, display, automated analysis, and reporting capabilities. In fact, the high voltage impulse analysis software provides fast and repeatable results in compliance to IEC international standards, including UP, T1, T2, and so on, as can be seen in the results window on the right. And the lightning impulses as well as switching impulses are analyzed, and the characteristic parameters are calculated automatically. Now, lightning impulses with either overshoot, oscillation, chopping, or a combination of the three are analyzed without user interaction, and waveforms can also be overlaid for comparison, for example, full and reduced, to determine any changes in their characteristics. There's also integrated pass and fail indicators with user-definable limits, and that's going to help you increase testing throughput and productivity, and you can also choose to use the existing standards or the new K-factor method. Now, additional information is available at www.hbm.com/power, including a KEMA high voltage lab case study found at the bottom of the page. You can also click on the HV, high voltage impulse testing link, for an overview of the solution, including a 4-minute video, plus a link to data acquisition solutions and isolation products, and even a link to frequently asked questions on the high voltage impulse analysis perception software found at the very bottom of the page. Just a quick reminder, for additional details on electrical motor or generator testing, you can visit our website, hbm.com/eDrive. For switchgear and high voltage impulse testing, visit our website, hbm.com/power. And in fact, you can actually see a list of upcoming webinars or any previous webinar you can watch on demand. You can visit hbm.com/webinars. And if you ever have any questions after today's webinar, please feel free to contact HBM Technical Support via email. You can email support@usa.hbm.com or call toll-free 1-800-578-4260. And I want to thank you for your time, and I think we have a few minutes for some questions.
Thanks, Mike. Everyone, as Mike mentioned, we do have time for questions. So if you would like him to respond, please type those into the Q&A dialogue in WebEx, and we'll take a few minutes and do those. I will be sharing Mike's presentation with everyone that's here today. In addition, we do record these presentations, and you'll receive a link to that recording on our website if you're interested to recheck some information or share it with a colleague. All right, Mike, let's see. You mentioned eGrid. Is it okay to sample slower than 2 million samples per second when measuring these signals?
Yeah, actually, what we do for the HBM brand products, we actually offer a 200 kilosample per second sampling rate. Instead of the 2 million, you can sample, for example, up to 200 kilosamples per second on every channel for eGrid applications, which is very cost effective since electric grid signals, they're much lower in frequency than eDrive signals. They're typically at a fixed fundamental frequency of, let's say, 50, 60, or 400 hertz. So then the sample rates can be lower.
All right. Can data and setups easily be saved and exported?
Yeah, absolutely. The most user-friendly data acquisition systems, they enable you to save data and setups for later recall. And then they also allow you to export data into many different formats. In fact, the HB brand automatically embeds the setups with the data, and it includes StatStream patented technology that enables quick recall and display of large gigabyte-sized files that can be recalled in just a matter of seconds. And it also has over 20 plus different exporting formats, including ASCII, Excel, CSV, and so on.
All right. You mentioned analysis and reporting can be automated. How easy is that, and can it be customized?
Yeah, by default, actually, after the data is captured, what the system does is it automatically saves all the data. And it saves all the hardware and software setups, including all the displays, into a single file so that it's all part of the data and the setups are all pretty much placed together so that, if you ever did recall your data, the setup file is right embedded with the data file. Now, it does this automatically, and in fact, it automatically calculates all the existing formulas and also automatically updates all the existing reports, which can be fully customized to, well, include any formula. And you can customize any type of a report, which can be easily created with any number of pages to include waveform displays, numerical results, pictures, logos, even user metadata that could be information such as the serial number of the device under test and the environmental testing conditions. In fact, you can even have the user automatically prompted to enter that information prior to the test, so it's included in the data file and the report.
Wonderful. Well, everyone, thank you again for joining us today. We hope you enjoy the rest of your day. And Mike, thank you very much.
Thank you, and have a good day.